Good morning, students. Is my voice audible?
Yes, sir.
So, students, we have completed 2 modules. Today, I will start third module and electromagnetic sensors. In this, we will see different capacitor type sensors and inductance based sensors and electromagnetic based sensors. Here we have variable capacitor, and a capacitor is a electrical device. In that, we will have 2 parallel plates, and they are separated by a dielectric medium. Okay, so the dielectric medium will not conduct in between those 2 conducting plates, and if we connect 2 conducting plates to a power supply to the positive potential and negative potential, they will get charged. Those 2 conducting plates will get charged, and that device will act as capacitor, and capacitance is equal to epsilon naught into epsilon r into A divided by D into n minus 1. N is the number of plates in a capacitor, that is a small n, and D. So what is the distance between 2 plates is the D, and A, how much area covered by both of the plates or opposite plates is the A, and epsilon naught and epsilon r is the dielectric constants of air and dielectric constants of that material. And here we have different types of capacitors. You can see in figure B, we have 2 plates. One plate is fixed, another plate is moving. One plate, one conductor is moving left and right. And in the first figure also, you can see one conductor is moving left and right. So all these are variable capacitors. In figure C, we have sector type of conducting plates. And in figure D, we have multiple plates. Half of the plates are fixed and remaining plates are moving. And in figure F, one plate is fixed or one conductor is fixed. Another conductor is moving top and bottom. So distance is varying. So like that, we can construct capacitor depending on the application in different patterns. Here we have another type of capacitor application, that is level measurement. If you place conducting plates in electrolytic liquids or conductive liquids, depending on the level of the conducting liquid, we will get different capacitances, so that we can estimate the level of the liquid in the tank. Here we have 3 figures ABC, and in these 3 figures, we are using capacitor to estimate the level of a liquid in a tank. And here we have another type of capacitors. C and D are the rotational capacitors or rotating capacitors. These capacitors are also called as differential capacitors. That means in one device, we will have 2 capacitors like C1 and C2. And one conductor is common for the both of the capacitors. So here you can see this conductor is moving left and right. So if it moves towards left, C1 capacitance will increase. Or if it moves towards right, C2 capacitance will increase. Here also you can see. So dielectric medium we have replaced with the moving object. Depending on the position of the dielectric medium, capacitor capacitance will vary. In figure C and D, one of the capacitor plate is rotating, another plate is fixed. Depending on the position of the first plate, we can estimate the capacitance so that we can estimate the parameters. Inductive sensors. Already we have executed linear variable differential transformer. So in that we have created a magnetic flux using primary coil, and we have moved core in the linear variable differential transformer. Depending on the position of the core, we will get different outputs. So here also we can see variable inductive sensors. In Lvdt, in primary coil, we have allowed current flow so that we got magnetic flux. If we vary that current, flux will get variation. That is called self-inductance. And if we allow fixed current flow in the primary coil, and if you place the primary coil near the secondary coil, we will get inductance in the second one, that is called mutual inductance. And the inductance can be expressed as L is equal to N into phi by I. N is the number of turns and phi is the magnetic flux generated, and I is the current which we are allowing in the circuit. And we have separate equation for the phi. Phi is equal to Fm by R. And if we substitute that phi value in inductance L value, L is equal to N square by R. And if you want to calculate R, we have the equation, and this is the equation. R is equal to 1 divided by A into mu R mu naught, where mu R is the magnetic permeability for the magnetic core inside the coil, and capital A is the area of cross section, and L is the length of the conductor which we are using in the circuit. Here we have different shapes of the inductive sensors. Figure A to D, you can see this wiper is moving in B and D, and A and C, you can see wiper is moving top and bottom. And in figure E, you can observe this is the circuit which is similar to our Lvdt device. Inside the coil, we have a magnetic core that we are moving. Coil is fixed and we are moving core. And in figure F, we are creating a mutual inductance. That means for one coil, we will give power supply and we will rotate this core. Because of this core movement or rotation, we will get inductance in the second one. And here you can observe G and E figures. In E figure, we don't have center tap. So depending on the core position, we'll get inductance in the first coil or second coil. By appearing, it can be one coil, but we have center tap connection in the figure G. So they will act as two. On the core position, we can estimate the inductance. And we have disconnected core here, and if we connect this core, we will get one type of inductance. Open this core. If we disconnect this core, we will get less inductance here. So all these figures are different types of inductive sensors. And the last figure also, if we move core top and bottom, we will get different inductance in the both coils. So these are the capacitive type of sensors, and these are the inductive type sensors. Eddy current sensors. Already in the we have eddy current definition. On the circuit board, if we have two capacitors, on the circuit board, if we have two conductors, and if they are acting as capacitor, even though they are not practically capacitors, physically they are not but they are lying near each other, so they are acting as capacitors. Because of that, we will get some magnetic flux, and that magnetic flux will disturb the main magnetic flux, and because of this, we will get some current flow. So these currents are called as eddy current sensors. So we can use that eddy current disadvantage to estimate some parameters. Those sensors are called as eddy current sensors. The inductive reactance of a coil supplied by alternating current decreases if a non-magnetic conductive target is placed inside its magnetic field. Instead of using magnetic material, if we use non-magnetic material, we'll get different in the magnetic flux. This is because the varying magnetic field induces eddy currents on the target surface that produces a secondary magnetic field which induces an opposing voltage in the coil. So because of the non-magnetic field, conductor will get disturbance and it will create another magnetic field. The closer the target is to the coil, the larger the change in the impedance. Ferromagnetic target materials first increase the coil reactance. Because of this theory is giving information about the eddy current sensor, students. So if we place a magnetic material or non-magnetic material near a coil, we will disturb the main magnetic flux because of this device magnetic flux. Because of that, we will get current flow in the devices. That current will be proportional to the magnetic nature of the object. So this property we can use to estimate the some physical parameter, displacement or rotation, angular displacement. You can observe eddy current proximity sensors. We are moving this object near to this one so that we will get eddy currents flow in the first one. Here we are moving internal object left and right so that we can get changes in the eddy currents. So we have discussed capacitor type of sensors. In capacitor type of sensors, so we have moved one conductor or one dielectric material to vary the capacitance. And in the inductive type sensors, we have moved core or coil. We have moved coil so that we will get variation in the inductance. In the eddy current sensors, we have moved one magnetic material or non-magnetic material near another current carrying conductor so that we'll get disturbances in the magnetic flux. That variation we can use to estimate the physical parameters. This is the device to estimate the liquid level and that liquid should be a metallic. And here we have another device to estimate the angular displacement. So if the liquid level is increasing in the tank, we will get variation in the eddy currents because that metallic liquid will act as a current carrying conductor so that it will create disturbances in the magnetic flux. So three types of parameters we have seen. They are capacitor type sensors, inductive type sensors, and eddy current sensors. I will show you some practical devices to understand the working of the sensor. Students, here we have eddy currents sensors. We have one device which is producing magnetic flux, and if we move this coil near the another device, because of this we will get another magnetic field and another current flow, which opposes the variations in the magnetic flux. So if we estimate this current, we can estimate the distance between these two, coil and conductive material. And all these images shows the eddy current sensors. And here we have inductive type sensors. And this is first one, that is capacitor type transducer. This is fixed plate in a capacitor, and this is movable plate. If you apply pressure here, you will get deflection in the diaphragm. Because of that, you will get variation in the capacitor. By changing the capacitance, or by getting the change in the capacitance, we can estimate the pressure which is acting on the another plate. So this is capacitor type transducer, and this is inductive type transducers, and this is eddy currents type of transducer. Next topic is Lvdt. Here we have construction. One primary coil, two secondary coils. Yesterday we have completed experiment. If we move core, we will get different output voltage in the primary, secondary one and secondary two, and output equation will be E out is equal to E1 minus E2. A variation on the Lvdt is the RVDT, that is the rotational variable differential transformer. One minute, students. Rotary variable differential transformer. This device works on almost on the same principle, except the core revolves on the shaft instead of moving in a straight line. RVDT can be constructed for limited motion of 360 degrees motion. So we have another device that is which is called as rotary variable differential transformer, and here core will move in angular. Core will move in circular path instead of moving in left and right or top and in linear pattern. So here we have two coils as it is in the Lvdt, and because of the core different outputs in the secondary one and secondary two. And observe this figure, I will explain.